Okay, so good afternoon, everyone, and welcome to the next edition of the Princeton Wireless Distinguished Seminar Series. We have with us today Karthik Sundaresan. He's a professor in the School of Electrical and Computer Engineering at Georgia Tech, and very recently, prior to this, he's been our nearby neighbor at NEC Labs America in Princeton, New Jersey, and research interests are broadly in wireless networking and mobile computing. And he is the recipient of SIG Mobile's Rockstar Award for Early Career Contributions, as well as holding over 50 patents and received business contribution awards for commercialization technology at NEC, including some infrastructure-free tracking of first responders technology. He's a fellow of the IEEE and ACM, and today he'll be talking about engineering networks in the sky. So I'll hand it over to you, Karthik.
Thanks, Kyle, for the generous introduction. Thanks, everyone, for attending this talk. So let me get it started. Can you see it full screen? All right. So basically, as Kyle mentioned, so what I'm going to talk about today is engineering networks in the sky. And basically, what are the challenges in going about this vision? And if we could accomplish this vision, what is the potential for such a vision? So this is going to be the outline for this talk. So what I'll do is I'll briefly introduce what are some of the drivers for low altitude unmanned aerial vehicle-based networks today that can provide on-demand mobile connectivity. I'll follow it up with what are the challenges in realizing such a vision. Then what I'll do is I'll present one of our systems, which we call Skylight, as a backdrop and use that to motivate and also to dig deep into what are the challenges in creating such a network. And I'll go further to conclude by identifying and highlighting some potentially interesting directions that Skylight can take us, not just in connectivity, but also in various sensing applications. So to start with, if you want to look at where our 5G networks are taking us today, so they're envisioned to cater to a whole bunch of services, quite diverse in nature. And it ranges all the way from industrial automation to connected transport, and even to various immersive services, right? And that's from the consumer standpoint. So we have both the industries and the enterprises, but we also have the consumers that's accounted for when it comes to connectivity. And so from a standpoint of like connectivity itself, so it's quite abundant, right? We have access to a lot of data rates, and there are lots and lots of interesting applications that are going to make use of these data rates. The slightly different interesting question is connectivity truly ubiquitous? And depending on who you ask, oftentimes the answer is really no. And particularly if you want to look at challenging situations such as large events or even emergency situations like natural disasters, oftentimes we find our cellular networks to be either congested or even the infrastructure itself to be compromised. So indeed, during one of the Indonesian earthquakes in the past, the cellular infrastructure was so badly compromised that the alert system that was there, that was supposed to send out text alerts to people in the coastal towns, was completely disabled. And that prevented from the alerts of an impending tsunami from getting to them. And that in turn eventually resulted in a lot of casualties. So this is not just one isolated incident. So with the growing impact of climate change, the severity of this problem is only bound to increase. Providing connectivity in challenge environments is actually an integral component of 5G's broader vision of providing safer and secure cities. In fact, if you look at the federal government's initiative, they've come up with the FirstNet initiative, whose sole purpose is deploying a dedicated LTE network just targeting first responders. And this is actually a much needed upgrade compared to the low rate voice services that they're using today. So this would be something dedicated for them. And AT&T is taking the charge on this. Now, this is a great welcome step. However, the inherent static nature of these networks still makes them vulnerable to all the natural disasters and other potential events that can come about. So what we ideally need is the ability to supplement these networks with an on-demand, rapidly deployable version that can cater to both spatially and temporally varying connectivity requirements. So these are primarily for challenging scenarios where you want to create something on demand quickly and then tear it down when you no longer need it. So to make this happen, our vision was to reimagine our existing terrestrial mobile networks. And the essential idea was, can we untether these terrestrial stationary mobile networks and instead host them on a network of UAVs that can adaptively beam on-demand connectivity to users on the ground? The essence of such a vision would essentially be to track, locate, and connect both the public and the first responders in challenging environments. So that's how this whole thing got started. Now, before we get into the details, let's take a step back and look at the bigger picture of various forms of networks in the sky that are coming up today. There's been a lot of advances in both low altitude and high altitude platforms. In fact, this is a very exciting time for these types of networks, and there's a lot of action going on both in the research space as well as in the commercial space. Now, at the highest altitude of around like 500 kilometers, we have the LEO or the low Earth orbit based satellite based networks. And some of the popular ones, or the two big popular ones in this space, being Starlink from SpaceX and Project Kuiper from Amazon. So these are meant to operate for years together at a time and are supposed to cover wide regions of the Earth. So it's basically going to be able to connect even remote parts of our Earth and provide connectivity to those regions. So then we come to the next level, which are called the high altitude platforms that operate at about 20 kilometers. We have two popular examples here. One is Google's Project Loan, that's balloon-based systems that leverage the air currents to position and move between different layers of altitude. And then we have Airbus's solar-powered Zephyr platform. And these are meant for several months of operation at a time, not in the year's time frame, but more in the month's time frame. And they still cover wide regions, not as big as the entire world, but probably regions as big as a country, something of the scale of that. And then if you come down much lower, we come down to much lower altitudes of, let's say, a few hundred meters. So this is where we find operators and federal agencies. They've been experimenting with several low altitude platforms. And these are meant for specific short-term private and secure deployments to cover smaller regions at the scale of cities. So we've gone from all the way to the world, to country, to the scale of city, right? And as we can see, these types of platforms cater to a widely different spectrum of applications. So each has its own role to play in different applications, in different types of endurance needs, and for different use cases. So what we wanted to do was, so we ended up focusing on the low altitude platforms, an example of which are like the rotary wing drones that are quite popular. And that's because they offer an edge when it comes to deployment and operation. So one, they require very little deployment overhead, right? You don't really require little to no ground support. You can fly these things autonomously at the altitudes at which they are targeted for. So it keeps the expense and the cost really low. The legal framework is very simple. It's easier to get a license to fly, and you can even run these autonomously. And today there's so much of off-the-shelf availability that we have very advanced like quadcopters and whatnot that have very sophisticated capabilities that can go beyond connectivity and do very advanced sensing as well. So you can mix and match various modules to create very interesting applications. And also the fact that they can provide secure, optimized connectivity and sensing is a big draw for operators. And they've been experimenting both from using these UAVs, both as base stations as well as potential clients. And as you can see here, one of the latest additions to Verizon's family was this Parrot Anafi AI drone, which is meant to be a client, but it has sensing capabilities to allow you to quickly use its LTE or 5G connection to send a lot of information for real-time analytics. So the next obvious question that arises is, how hard is it really to beam LTE or let's say 5G NR from a UAV, right? Isn't it as simple as just mounting a 5G radio like you see on the picture here and just letting the drone fly? Unfortunately, the reality is much more complex. As you can even see in this figure, while the radio is mounted on the UAV, it still continues to be tethered to a core network unit on the ground to be able to provide the cellular service. And that could end up potentially limiting the flexibility that comes with the mobility of the UAV itself. To see why this is challenging, we need to take a step back and look at the architecture of cellular networks to begin with. So, and the cellular network essentially consists of three main components, right? So we have the static but extensively planned radio access network, or the RAN as it is called, and that's essentially what people see. So when they think of a cellular network, the only thing they think of is the device connects to a cell tower, and that basically is the cellular network. Of course, it's an important part of the cellular network, but behind the RAN, you also have what is known as the core network. And the core network is a very critical part. It's a monolithic network of a lot of network elements, which have a lot of standardized interfaces, mainly for a lot of legacy reasons. They've gone through various versions from 2G, and now we are at 5G and people are talking about 6G. So when you go to 6G, it doesn't mean you decommission the entire 5G and jump to 6G. You have to provide backwards compatibility to a lot of the devices that operate on prior generations. And so these interfaces have grown over time and they've become so complex, and yet they are so critical in terms of several important functions like mobility, routing, policy enforcement, and whatnot. And you also have the final piece, which is the backhaul transport network that connects the access network to the core network. It's a high-speed, reliable wired network between these different elements, and that's essential for eventually getting all your traffic between these elements and eventually to and fro from the internet. So it's always assumed to be a reliable piece of a network. Now we can imagine deploying such a heavyweight cellular stack. If you want to take that and deploy it on resource-constrained UAV platforms, this is a fairly daunting task. And the challenges are going to cut across all layers, not just one layer. It's going to span across the RAN, the core, and the backhaul. So towards addressing these challenges, what we did was, so we designed and built one version of a solution. So the design space is quite broad, and there are a lot of points in which you can operate in this design space. So we picked one version. And what I want to do is, and we call the system Skylight. It's in some sense, it's a first of its kind on-demand self-optimizing 5G network that is hosted on UAVs. And you can think of Skylight as something that could either augment existing terrestrial networks where you need additional capacity, but the bigger agenda for Skylight was to provide a standalone self-contained network that can provide connectivity and sensing capabilities, even when you have absolutely no connection to the existing terrestrial infrastructure. So that was the main goal behind the design of Skylight. And as a result, so we were targeting main applications in the context of public safety, but by the nature of it, it also expands itself or extends itself to other tactical operations in the defense segment. So at a high level, it consists of, it's a very modular design. It consists of three main modules. So we have the SkyRAN, which is responsible for providing a self-optimizing small cell that autonomously instructs and positions the drone to cater itself to the traffic distribution that it sees on the ground. The second piece is the SkyCore, and the goal of this entity is to provide a really lightweight, completely distributed, yet fully functional core network that can be run on very resource-constrained UAV platforms. It's like taking the complex core network and somehow putting it on each of the UAVs. And the final piece is the SkyHawk, which is responsible for connecting these different UAVs through a robust high bandwidth gigabit per second backhaul network that can serve as providing the transport between both the UAVs as well as between the UAVs and a ground station if need be. So we ended up building out the system with a few UAVs, about 4 to 6 UAVs that could be autonomously deployed in the NEC campus. And we ended up designing our own payload stack and interfacing it with the UAV's autonomous flight control. So the idea was to remove human from the loop so that once we deploy these networks, they're automatically able to sense the traffic distribution on the ground and appropriately position themselves and adapt themselves as needed. So what I want to do in the rest of this talk is use this Skylight system as a backdrop to mainly motivate what are the challenges in designing such a system. And then if we can accomplish a design, what potential does it have for the future? So I want to start off going into each of these pieces a little bit to give you a little bit more insight behind the challenges in each of these modules, the RAN, the core network, and the backhaul network. And eventually I'll talk about some applications beyond connectivity that the system can enable. So if you have any questions, we can have them in the chat. I can take some questions now, or we can do a little bit. I go a little bit more into the details, and then we can do that as well. Let me see if I can see. Yep. So I think I'll carry on. And then if I see any questions, so I'll take them up as and when I take a pause on these.
Yeah, and I can alert you as well, Karthik.
Yep. Okay, that's great, Kyle, because I probably have to click somewhere else to look at the questions. Okay, sounds good. So let me start with the first component, right? So this is SkyRAN. So the goal of SkyRAN is essentially to provide a self-configuring small cell access network, right? And how do we do this? Now, of course, now we have UAVs, our base stations are no longer static, right? So we have the power of mobility, right? It gives us a lot of flexibility. But with this flexibility, it also brings another layer of complexity. So what do I mean by this? Now here, what I show is I have two graphs here, right? The graphs here essentially capture the UAV to the client device, which is called the UV, user equipment. It basically captures the throughput on this link during a UAV's flight at about 100 meters altitude, right? As you can see, even for a single device, the path loss can vary significantly by over 25 dB depending on where the UAV is in its trajectory. And the throughput can be over 50% in more than half the locations, right? Based on the terrain conditions and the UAV's position. So depending on where you operate, there could be a huge difference in what you could have potentially achieved as opposed to what you would achieve depending on where you are. Now, this is for one UV, right? Now, typically a cell serves like several tens of UVs. And so the question is, how do you figure out where you want to place your UAV in the first place and what kind of measurements are needed to make this intelligent decision? So we need to position the UAV in the airspace. Ideally, what we would need is we would need to measure the path loss or SNR to the UVs from all potential points in the 3D airspace, right? So that would allow us to create what is called a radio environment map or a REM, similar to the one you see in the graph here, right? It captures the UAV's positions sort of projected on the 2D, showing the locations that offer at a particular altitude, offering good and poor throughputs, right? For a given user's location, what are the different places or positions in a particular altitude for which and how the throughput varies, right? Now, these maps are useful only if we know the location of the users for which they're created, because you don't want to be creating these maps every so often. You want to incrementally build these maps so that they can be used to predict future decisions. There's another challenge as well. If the flight time needed to measure and create these maps is large, then these maps would soon become stale with user UE mobility. So the users are mobile, right? And of course, short-term mobility, you would expect the link adaptation to take care of it and adapt itself, right? But if a whole cluster of users move, like for example, in a firefighting scenario, the first responders move from one region to another as the fire moves, then the whole cluster moves. So you need to be able to estimate these conditions in an adaptive and on-demand manner so that you can adapt your positioning as well. And the graph to the right here essentially shows how a fixed position of the UAV soon becomes suboptimal and starts degrading in performance as the fraction of UAVs starts to move, right? And once they start moving appreciably, then the position is of course no longer optimal and you would start suffering in throughput. So there is a trade-off in how often you take measurements and how long you spend providing optimized connectivity. So what Skyline intends to do is it adapt itself to provide optimized connectivity across multiple users jointly. And it does this through three particular steps. So first, it localizes the users as accurately as possible and as quickly as possible using a very short flight trajectory. So it takes a bunch of measurements and quickly localizes them. Then it computes an intelligent flight trajectory, just particularly for the purpose of taking measurements, so as to quickly estimate these radio environment map to its users. So it wants to collect a little bit more measurements, but how do you compose this trajectory so that you get as accurate a map as possible? Of course, if you spend a lot of time, you'll get a lot of information, but it also becomes obsolete soon. So you need to strike a balance in where and how you prioritize the regions where you want to take measurements on. And finally, based on the maps that you create, it figures out where to move and position the UAV in a particular point and provide optimized connectivity for a substantially long period of time until it's deemed appropriate that things have changed significantly on the ground that you need to take another set of measurements. So now let's take a little bit deeper look into each of these components, right? Now, what does it do for localizing users? So what it does is it leverages the synchronous nature of cellular networks. So the good thing is the base station and the UEs are synchronized. They are in the same time frame of reference, and this can be leveraged to estimate the time of flight based on the UE's uplink transmissions, right? There are a lot of existing reference signals in cellular transmissions. So these reference signals on the uplink, they're called the sounding reference signals. You can leverage them and use them to obtain time of flight, right? Then you can leverage the mobility of the UAV itself to create some sort of a synthetic aperture where the UAV measures the time of flight to the UV's transmissions from multiple vantage points in the space and uses that to enable multilateration and other techniques for localizing the UVs. Then what you can do is you can put all these measurements together and along with some signal processing techniques to alleviate time offsets that still creep in, and you can increase the resolution of the estimates, and eventually you can try to get some good form of localization accuracy. So when we did this, so we used a 10 megahertz channel, LTE channel, right? And even with that 10 megahertz, it was possible that we were able to get to 5 meters median accuracy. Of course, this might not seem great, but from the perspective of creating radio environment maps, this was still quite useful in creating reasonably accurate radio environment maps. And today you have carrier aggregation in LTE where you can easily aggregate up to 100 megahertz. And with 5G, you have access to much larger bandwidths, and you have much more very specific reference signals just for estimating the distance as well as the angle of arrival and whatnot. So in future, you'll easily be able to do sub-meter with cellular systems, and that's only going to help us make our radio environment maps much more accurate. Now, going back to these radio environment maps, so we want to take measurements from a large number of points in the 3D airspace to create these maps, right? That's the ideal solution. But of course, we don't have the time to spend on taking all these measurements because the users could potentially be mobile and they could be moving around. So the goal is to balance accuracy versus overhead by making the UAV prioritize and explore specific regions of high entropy with respect to this construction, map construction, right? So you want to identify regions where there is much more uncertainty, that it makes more sense for you to visit those regions and collect some measurements. And some of the other regions where there is high certainty, you can potentially interpolate using a host of other available techniques that are out there, right? So we want to be able to generate a reasonably accurate REM within a short amount of time. So time is of the essence here. At a very high level, the details are not important here. So whenever you want to collect a set of measurements, what it does is the UAV computes the signal gradient maps based on the existing REMs that are available from all the UEs put together. Then using the signal gradient maps, it determines which are the high gradient clusters. So which are the clusters or regions in the airspace where there is a high uncertainty in terms of the measurements. So then it figures out a flight trajectory that maximizes the information utility in covering all these clusters. So utility here essentially refers to the information that is gained by the trajectory by visiting new regions with respect to the length of the trajectory, which is the overhead, right, or the cost that is involved. So once the measurements are done, the maps are put together, the maps corresponding to the locations are updated, because this could be used for other users, because a user could move out of a location, but if I've indexed these maps with respect to different locations on the ground, I could use it further for providing connectivity when a new user moves into that particular location. Now you can enhance the resolution of these maps by a host of other interpolation techniques. You can also create some pre-trained generative models to provide high resolution from low resolution maps. So these are all different techniques you can add on top of what we already have to further increase the resolution of these environment maps. And of course, this process repeats over time. So if we were to evaluate this performance, so we have access only to a limited campus testbed, right? So it has a building blockages, it has a forested area, it has some open space. It's a fairly decent environment for a testbed. But if you want to really evaluate it for much larger cities, much more urban environments, so for which purpose we used a 3D simulation of New York City based on the 3D environment maps that are available in the public space. And we use both these together to understand how well our solutions can scale. So if you look at the figures on the left, they show the REM or the environment map, radio environment map that's created by Skyran, right, in real time. That is used to position the UAV in a particular optimal position as deemed by the solution. It also shows that while users' location is important, just going with the location without creating the map is not sufficient. Because oftentimes, if you, for example, if you were to just pick the centroid of the user's locations, that will give you a potential solution, right? But oftentimes, depending on the environment and the terrain, that's not necessarily the optimal. So building this map does buy you quite a bit, at least 10 to 15 dB more on top of what a simple location-based solution can offer. Now, the graph to the right now, it shows that how long does it take to create a map, right? So we are able to create, it's not the, so if you were to consider an exhaustive trajectory, right? Like the users are all static and you spend enough amount of time collecting all points from all positions in the airspace, then of course you would get a really accurate radio environment map, right? So what we show is by picking in an intelligent trajectory based on the approach I mentioned, you can get to within 3 dB of this optimal map. And you can do that in under 1.5 minutes, right? So the goal is you spend 1.5 minutes in measurements. Ideally, you want to spend at least 10, 15 minutes, an order of magnitude more, and actually operating in that position for providing optimized connectivity. And of course, as these algorithms become better in the future, The goal is to push down this 1.5 minutes to under a minute, and however short we can keep it. Now, creating these REMs obviously has a benefit. It allows us to provide or operate in a position of optimized connectivity to all its users, delivering twice as much throughput than what you would have otherwise done if you were to just take a location-based approach. So you just quickly figure out the location of the users and position yourself. That's a perfectly valid solution, but it leaves a lot more on the table to be leveraged, right? Which you can, if you act to create these REMs intelligently and use them to further inform your decisions. So that's one of the takeaways for how do you create these self-organizing and positioning small cells in the air. So that was essentially what Skyran was able to deliver as part of the Skylight vision. So that brings us to the next piece. But before I go there, if there are any questions or if anybody wants to ask a question based on what we just talked about, this would be a good point.
Yeah, so I'll kick that off, I think. If anyone has questions, please put them into the chat, and then I'll read them out. Or if you would prefer, you can send me a placeholder in the chat, and you can unmute if you like as well. So I have actually a couple of questions about this. So I imagine that very different things happen on different subcarriers for each client, actually. And so I could have missed it, but I didn't see a discussion of doing something different on different subcarriers. So do you think also you said you had a gradient or a measure of uncertainty so might that also capture what happens on different subcarriers, or is there a possible extension to being very specific to different subcarriers?
Yeah, great question, Kyle. I didn't go into the details. So there are two separate things that operate here. So one is the decisions that the UAV's positioning is done for is based on average conditions of the users, as opposed to very specific, because we want to pick a position that's sort of good in the average sense across an aggregate of UEs, as opposed to optimizing the instantaneous channel for each of the UEs, because that's where we have link adaptation, right? We have a lot more sophisticated things you can do on a per frame or on a millisecond basis, where subcarrier level diversity and all the other things can be leveraged. So obviously we will not be able to, so that's why we decouple the notion of the optimization of positioning the UAVs from the instantaneous link optimization of the individual users. So the UAV is positioned from sort of if you were to define an average throughput or an average SNR basis.
Okay, but fair enough. But I could imagine. Sorry to interrupt you. I could imagine if the optimization algorithm had access to all of that subcarrier information, it might make certain trade-offs based on co-concurrent, co-occurring things going on. But let me just move on to another quick question, and I'm sure there's others. But the radio map, so whenever we hear radio map, we think to ourselves, based in all the work on localization, whenever we hear radio map, we think to ourselves, how are you going to maintain the radio map, and what happens when objects in the environment move and change the radio map? So how do you cope with that?
Yeah, so great question again. So as I mentioned, right, so there are a lot more details behind how the maps is created. So these maps are incrementally created and updated over time. So so it's indexed based on a location, right? And you deliver throughput based on the maps that you create, but you also keep incrementally updating, because there is a decision epoch, right? You take measurements, you operate based on the decision that came out of this measurements for 10 minutes or so, 15 minutes, and then you take another set of measurements, right? So as you keep doing measurements, you take also the timeliness of the maps that you have. If there is a region that you hadn't visited for a longer amount of time, then that information becomes stale. And so if the next time you visit that location, if something had changed in the environment, so that becomes your more prioritized or weighted map for that particular location. So that's sort of the way in which this evolves over time. So it's not statically fixed. So it's something that keeps evolving over time. So that's also one of the reasons that you take measurements and you want to leverage those measurements to provide some form of optimized connectivity in the next epoch. So you don't want to spend too much time taking those measurements because, as you said, if by the time you took it and you took a decision, if something had changed in the environment, then that's going to impact, right? But for things that impact you on a fast fading or a small scale fading basis, right? So that's where we let the link adaptation do all the sophisticated things it does, right? So this is not meant to interfere with that. This is meant to operate at a coarser time scale compared to the fine time scale of all the link layer adaptations that happen.
Okay,
I
thanks.
have a quick question here.
Oh, yeah.
So the 2 dB difference in power that you showed was quite interesting. So do you think maybe part of it was because of the self-blockage of the drone itself? And is there a way, is an optimization on maybe placement of the radio on top of drone, or maybe like putting a multiple of them to get diversity can maybe perhaps help?
Yeah.
What is the trade-off that we can see here?
Yeah. So I think from a design perspective, there's a lot of room to take this problem in different directions. Like, how do you close the gap, right? And so there are 2 ways you can look at it. One is you can think of like more sophisticated techniques or bring in diversity with multiple entities catering to the same region, so that you use the same cost in terms of time, but you get a much more sophisticated map. Or you take a simpler approach, keep it distributed, lightweight, but then you take longer time, but that has its own trade-off in terms of the usefulness of the information as well. So you can take this in different directions. You could use different drones, but the way we envisioned this was, so each drone is going to be like a small cell trying to optimize. So if you are planning to deploy it over, like, let's say Princeton with like 4 or 6 drones, right? So then each of them is going to take care of a certain region of this coverage, entire space of coverage. And each of them is going to figure out within its responsible coverage space, how do I take measurements and optimize for? Of course, now if you want to deploy more drones within that region of space to help get a better map, yes, I think you'll definitely gain with the diversity you get from that. Because it's not just the self-blockage, but it's also the fact that we want to keep the time to get this map as small as possible. So which means that there is a bit of interpolation that happens in a lot of regions. And if suppose those regions were classified wrongly as high uncertainty regions, right? Or vice versa, right? Then you're potentially missing some useful information by skipping those regions. So that's what leads to this gap, right? Yeah, so definitely there is a lot of room to take it further.
Thanks.
So I'll probably keep going to the next piece and then we can come back. All right, so let's move to the second piece, right? The second piece in Skylight is SkyCore. It plays a very critical role in orchestrating the machinery behind our mobile network, right? That's the role of core network. It's something that people don't hear much about. And here the role is, it's more of an architectural innovation and a lot of engineering that goes behind it. And yet it is still critical to holding all the pieces together in Skylight, right? So it's not the most jazzy piece, but it's in some sense the most critical piece. And the way SkyCore is designed today is it's a complete antithesis to how core networks are designed. And this is taking this radical view, particularly because we want to deploy it for dynamic and inherently unreliable environments on these UAVs. So what is the core network, right? Most people are not aware of what the core network does today. So it's called the Evolved Packet Core for LTE. And in future, you will have also a standalone core for 5G. So there are different versions of it, right? But at a high level, it's that part of our mobile network that handles all the essential functions relating to routing, policy control, quality of service, mobility, authentication, etc. So it does a whole bunch of functions, right? You don't need to understand the jargons and the acronyms. They're not important, but just the fact that it handles a lot of control and data plane related issues for us in making our connections and content go through. Now, if you were to take today's solutions, now the biggest question for us when we deploy a network on UAV is, where does this core go? Where do you place this, right? The simplest solution you can think of is you take the EPC. It's a straightforward application, right? The way today it's envisioned is you have an EPC that is connected by a reliable wired network. You take the same approach, right? The LTE radio is mounted on the UAV, or your new radio, NR radio, is mounted on the UAV, and the EPC itself remains on the ground. And it is tethered to the radios by a reliable wired connection like the ones you see here, right? I mean, of course, it is a possible solution, but as you can very quickly see, it completely limits the flexibility of the number of UAVs you can deploy and also how flexible you can use them for the purposes. So a slightly better option is to make this EPC to the radio access network link as wireless, right? This will allow the EPC, it's still on the ground, but it allows you to control multiple UAVs in a scalable manner. Because today, if you take an EPC, it controls an entire section of the country. All the base stations in one section of the country are run by one EPC instance, right? So that is possible, right? So this would allow you to do that, right? Except that now we have wireless on the critical path. We no longer have a wired connection. We have a wireless connection to the radio access network. Now, if you make wireless in the critical path, you need to understand that your EPC sits in the critical path for moving every packet between devices, right? Any packet that goes to the network, or if you want to even talk to another phone within the same cell, it goes through the EPC. So the unreliable nature of the wireless link between the EPC and the RAN will soon become the single point bottleneck of this entire system, right? And now you have to go through the vagaries of the multipath wireless channel that impacts link performance, as you can see in the graph above here, right? So it just simply shows that as the UAV moves, at one point you're in a line of sight channel to your user, and immediately in another point you're on a non-line of sight, there is a foliage blockage or some other blockage, and you immediately lose quite a bit of throughput and performance, right? Now, how does this impact? So with respect to application performance, this in turn leads to a significant number of control plane transmissions within the core, right? Now, these control plane transmissions are very critical to establishing your session. So if they fail, then it ends up affecting all the time sensitive control loops that run behind the scenes that are very inherent to the cellular protocol state machine. So what it ends up happening is you'll see longer delays on your mobile device handset, right? And this is something that we have to be aware of when we put EPC to the RAN link on the wireless. Like putting wireless on the critical path really has this impact. So we can think of a completely alternate version, right? The previous options basically resorted to leveraging the existing EPC, and hence it required it to be on the ground. Now, what Skycore does is it says, why should we have to have this restriction? Let's explore a completely radically different architecture whereby we would like to push it to the very edge of the network. Namely, we just host them directly on the radio access network or on the base station itself. So essentially, the EPC and the RAN are on the base stations and directly hosted by the UAVs themselves. Now, the obvious advantage is that it completely eliminates the unreliable wireless link between the EPC and the RAN. Oops. On the other hand, it also brings with it its own set of challenges, right? Because of the fact we've decided to go in a completely opposite direction to how core networks are designed today, we've really said that it's no longer a core. It's in some sense, it's an edge version of the core, right? So how do we actually go about designing it? It brings a specific set of challenges, right? We are now asking for a heavyweight EPC deployment. It's meant to handle a network of base stations, and we want it to be run on each of the edge units, namely the resource constrained UAV platforms. So this is going to have an impact on both the battery lifetime of the UAV as well as on the control plane latencies, right? For very critical connection events. Like in this particular graph.
Sorry, Karthik, I just have a quick clarification question.
Yeah.
So is this intended for traffic from drone to drone, or is this intended for traffic that goes back to the central core network?
Yeah. So today, right, if you want to use your handset, like even if, like, let's say you and Yasman want to talk on the LTE connection, your session is established through the core network. So the packets do go through the core network, right? So in that sense, anytime a device wants to connect, the EPC is always in the path. So it will go through, even if you want to do drone to drone. I mean, if you want to do drone to drone, you can do other ways, right? So I'll talk about it later on, like between drones, what happens, right? But anytime your devices are involved and they want to use their LTE or NR interfaces, it will go through this EPC path. And so what happens is there are a lot of, like whenever a connection goes, your phone goes into idle, it comes back into active mode, right? So there's always an attach, detach, a lot of events that happen behind the scenes. And now if you want to handle all these events, it requires a lot of compute capability on the drone, which the drone doesn't have. So just taking the EPC and putting it, you can see that the control plane latencies are really going to shoot up, right? So which means that the user experience is really going to suck, right? And not just that. So there is no communication between EPCs today. And that's because an EPC is meant to handle like a section of the country, right? So nobody travels, people travel between base stations or a network of base stations. People don't travel from the East Coast to the West Coast often, right? Like on, for example, you don't expect connectivity seamless as you go from the East Coast to the West Coast within a matter of hours, right? So when that happens, people just break and make connections. So there is no notion of inter-EPC communication for handoffs today. And in our case, if you were to go with this design where you push the EPC to the edge, what ends up happening is you create even a simple base station to base station handoff into an EPC to EPC handoff. And this is something that's not possible in the core today, right? So these are really some of the challenges that we bring about by going for this design, right? And yet what SkyCore intends to do is it still advocates for this radical edge design, right? Because we believe that the advantages really outweigh the challenges, right? And it's essentially, it's the best in the best interest of these unreliable and dynamic environments. It does make sense for us to put this edge on, put this core really on the edge on the UAVs. And with some design decisions, we can really address some of these key challenges that come about with this design. So it relies on two key design innovations, right, that are built on software-defined networking and virtualization primitives to overcome the key challenges, right? At a high level, what it does is it completely refactors in software all the core EPC's functionalities so that we can recreate a lightweight design that can be directly hosted on each of the UAVs, right, just with a single board computer. So we put a single board computer on these UAVs, but then we are able to run most of the core functionalities that is needed by our LTE network today. Because we can't cheat the system, right? If we change anything in the core, your users' devices will not connect to the system. You will not be able to make a call. You will not be able to connect to the internet. So there's no way you can cheat the system unless you really create a core instance that provides all the functionality. So how do you refactor this whole thing in software such that it's completely lightweight, so such that you can put it on each of these UAVs? And two, how do we enable efficient communication, both in terms of protocol and new interfaces between EPC instances so that we can enable routing and mobility management? Because one key aspect to note is that one of the biggest advantages of a core is it has the centralized view that gives you seamless mobility when you go and hand off across base stations, right? But now by pushing things to the edge, we lose that. So how do we compensate for that and yet provide mobility in a low overhead manner? So these are the two key challenges that we address in SkyCore's design. So I think the details are not important here. So I'll just go over very high level stuff. I'm sure you'll have a lot of questions and we can take this offline later towards the end of the talk, because this is kind of very domain specific. So I'll just touch upon some of the very high aspects of it. So what I mean by software refactoring is what it does is it starts by decoupling control and data plane functionality, right? And we were doing this like 3-4 years back, but today it's the norm, right? If you look at the new initiative in terms of moving the core to the cloud, that's the first place you start. How do you create a software version of this core network? And how do you decouple the control and the data plane? The next thing we do is we create lightweight SDN-based applications that are used to replace the legacy control plane functionality, right? So we replace them with very lightweight application agents, but we also create new applications that are specific to the UAV, the dynamic environment context. For example, if a UAV has to go down for a recharge, then basically the state and the users it serves needs to be handed over to another UAV that's going to replace it. So you need to have new applications that are responsible for taking care of these operations. So we created some new applications that are very specific to UAV control in terms of interfacing with its autonomous control, with its battery capabilities, and things relevant to the UAV itself. And for security and policy enforcement elements, we replace them with pre-computed in-memory data stores so that the transaction delays that are incurred are highly minimized. And finally, when it comes to the data plane, we replace all the heavyweight tunneling protocols, signaling protocols, and distributed data plane elements with a compact SDN switch that allows us to keep the overhead low, but allows us to also scale up in terms of the line rates we can provide on these networks. So for inter-EPC communication, what we do is we create two virtualized network layers that employs SDN-based overlay routing on each of them, one for the control plane and one for the data plane. And one key difference we make is, like today, what happens is whenever you create a session for a UV, you have something called tunneling protocols. And those tunneling protocols are heavyweight and they incur a lot of overhead. Now in the UAV context, it doesn't make sense to create a tunnel per UV, right? Because the users are going to be mobile. The base station itself is going to be mobile. So which means you're going to incur this overhead again and again. So you don't want to do that. So we remove this whole notion of GTP tunnels And then we create segment-based routing where tunneling happens on a segment, on a link basis, where all the connections that need to go through between a UAV to an UAV link are aggregated within the same segment. So in some sense, we are amortizing the overhead on a segment basis as opposed to a per user basis. And this allows us to really scale when operating on these resource constrained platforms. So we also enable proactive synchronization of user state, which includes users' location and security and policy updates. We proactively understand and migrate the state from UAV to another UAV so that we create a stateless and seamless mobility scenario for users when they go between UAVs. So these are all things that we had to create new because of the design decision we made in terms of going for this edge design, because we didn't really want to have wireless in the critical path of any of these transactions. And that really paid off in terms of creating something that was quite robust to all the mobility that these networks go through, right? If you were to take a naive edge EPC solution, right? So you take an EPC and then even if you could have a very sophisticated server hosted on the UAV, and if you take the EPC and drop it on that UAV, you will still have to drop connections and reinitiate connections as users move between EPC instances, because that's something that's not available today, right? And as you can see here, this was an experiment where the user moves from one UAV to another. He walks on the ground and there are two UAVs covering different regions. And as you can see, the connection is broken and then made again with the other drone when there is a significant difference in its signal strength. Now, when this happens, it takes about 2 seconds, right? And that's because today there exists no inter-EPC handoffs, right? So with the new interfaces that we create, we are able to accomplish this at the order of like 100 milliseconds, right? And this is in the same granularity at which base station-based handoffs happen today. So it is possible, like the versions we create are able to manage it, at least for small networks. We can still cater to the mobility of users without any additional overhead. And the lightweight design of SkyCore itself, it is well suited for resource constrained platforms, as you can see in these graphs, right? It incurs 5 times lower compute utilization so that you can put it on low powerful single board computers on the UAVs, which means that it can support as many more connections and events, right? And it can do so at 9 times lesser control plane delays compared to a straightforward edge EPC solution, right? By keeping it lightweight and yet functional, we are able to scale much better to a lot more connections and do it with much less compute utilization so that we can hit line rates of gigabits per second traffic through the core to make good use of the backhaul capacities that we have. So these are some of the advantages that come from this design. Of course, the challenges required us to create a lot more design principles and design components, but at the end of the day, it was worth it because in these unreliable environments, you do not want to put wireless in this critical path between the RAN and the EPC. And so that necessitated this whole edge version of the core design. And this is one instance in which we realized it. And this had some pretty good performance in terms of being able to actually support connections and provide handoffs. So we were able to do handoffs between users when they go between UAVs, and they were using commodity LTE smartphones when they were running these experiments. So this is, as I said, so this is more of an architectural piece and a lot of engineering behind the scenes, and yet it somehow forms an important glue when it comes to deploying a cellular network. So I think this is again another point where I think we can take some more questions before I move to the last piece.
I'll just kick it off with a quick question about mobility. So I'm not very well versed in handoffs. I wonder, is there any commonality with what you've done and edge network designs for 5G network, edge network designs for very high user mobility, like users on a train, for example, when you want to hand off between base stations very quickly? That's the first question. And then the second question is, you mentioned that you're achieving a handoff of 100 milliseconds, which is equal to the status quo. But I guess the question is, why doesn't the status quo? I think you may have explained this, so maybe I'll just ask the first question actually. So the user mobility.
User mobility, yeah, great question, Kyle. So I think these are in the works. In terms of, like, even in one of the previous projects we did was we have what is called edge computing today, right? Mobile edge computing, and the whole notion of edge computing is you still have the core, right, sitting somewhere centrally, but then it has the ability to control or offload some of its functionality to the edge that's closer to the base stations, right? So that's one of the ways in which people take care of these high-speed mobility, or at least that's the envision, right? You don't have like really good solutions today, even for high-speed
That's
mobility,
what
right?
you're
Sometimes,
doing. That's exactly what you're doing, right? Correct?
yeah, exactly. So edge computing, so there are two versions, right? So you can think of SkyCore as the extreme edge computing solution, where there is no connection to a central core. Everything is really on the most edge point or compute point, right? But edge computing solutions are one step, they serve as a middle ground between today's core and SkyCore, for example, in the sense that you have a distributed core where there are central elements that are sitting in some central entity, but there are also edge elements that are closer to the base station when you want to optimize for lower latencies. So those, some of the mobility functions will be offloaded to those edge elements so that you can keep lower latency. So that is possible, right? But what we are talking about is you don't even have access to that centralized core element that can coordinate these different edge elements. So everything is completely distributed and edge, and still you want to somehow provide seamless mobility between these different edge elements. So that's sort of the extreme design space point that we wanted to look at.
I have a follow-up question.
Yep.
So I guess this distributed EPC makes a lot of sense actually in the UAV, now that you are mentioning it and I'm thinking more about it, because you typically have these UAVs flying closer to each other compared to the distance between each UAV, like in a ground station, right?
Yeah.
But does that mean that you actually want to always have a line of sight pass? Like you really want to guaranteed connectivity between these EPCs so that you don't fail in like handoff, right? So what is it that we are sort of imposing in the wireless link between these distributed EPCs?
Right. So you can think of it in the following way, right? If you were to compare it to other options, right? So there is, so the problem you are pointing out is common to what Skylight does, and it's common to even if you want to have an EPC on the ground, right? Because it's an even more disastrous of a design, because now we have to come back to the ground, right? And there potentially the ground to the air link itself could be blocked, right? And so you'll have to think about all other ways of, and it's a single point bottleneck, right? So definitely this has a lot more benefits. But that being said, even between the UAVs, like the UAVs could go around buildings and stuff. So you might not have a connection from one UAV to another at times. And what happens in those handoffs, right? So those are things. So Skyhall handles partly some of those issues in terms of creating this topology so that you maintain connectivity. But non-line of sight with respect to handoffs between the UAVs is not something that has been addressed yet in Skylab. So Skyhall will touch upon it a little bit in terms of like the way it is designed, how some UAVs take care of application and some UAVs are purely responsible for the backhaul. So the good thing is you have the ability to move, right? You have to balance the access versus the backhaul performance when you move these UAVs. And that's the problem you're getting at. And I think that leads us nicely to the next part of the talk.
Okay, I'll just interrupt Karthik with a very quick question. We have one from somebody in the chat. So they're asking, how does secure access control work? What would conventionally be called SIM management? And more generally, how is the EPC managed?
Yep. So right now in the deployment that we do, so it's sort of managed based on prior keys and prior policies. So the SIMs are preloaded for the devices that we deploy, because we were planning this for like city scale networks where we have SIMs that we have access to, or the registration IDs and stuff. So these are preloaded onto some of the databases we host on our EPCs. So that's essentially how it is managed. And that also allows us to authenticate and do things quite fast, because we are envisioning these networks for like quick rescue operations, public safety operations at the granularity of an hour or two, not for like long durations, because today the drones are limited because of other reasons for operating for longer durations. So that's how today the EPC is managed. So it's sort of pre-configured in terms of access restrictions, and then the rest of the management happens dynamically in terms of migrating policies as well as state between the UAVs seamlessly.
Okay.
All right. So So Kyle, just a quick time check. How much time do I have?
So I think we said maybe 6 or so more minutes before we start.
Okay. So then let me just wrap up this part quite quickly. I don't want to go into too much of the details, but this is an interesting piece for people like who are focused on millimeter wave and things like that. So I'll just quickly go over it just to identify some of the challenges. There are still some open problems in this space that some of the future researchers could look at into these, right? So the final piece in orchestrating this network of UAVs is that we need a backhaul transport, right? And we are talking about connecting a bunch of small cells. So each small cells can easily generate a couple of 100 megabits per second. So we are trying to create a gigabit backhaul that can robustly provide connectivity between these UAVs. And that's essentially the role of Skyhaul, right? So how do we do this, right? So the challenge is that the position of the UAV, it couples the optimization of the access and the backhaul performance, right? Even if they were on two different technologies, like you're running LTE on sub-6 on the axis, and then you're running millimeter wave in 28 gig, or you're using Wi-Fi 60 gigahertz, whatever, right? Although they are on different channels, but the fact that your UAV's position is coupling the access and the backhaul makes it tricky, right? What could be a position that's favorable for one might be detrimental for the other. So you need to be cognizant of that in your design, right? And the other thing is, oftentimes as you go to higher frequencies, it's great because we have access to larger bandwidths, right? And that's why we want to go there, because we want to support a larger capacity on the backhaul. But the antenna arrays often have a limited field of view, right? So it's very hard as you go to higher frequencies to create an omni pattern, right? And not just that, oftentimes a lot of these radios we've played around with, commercial radios, they have like 150 160 degree kind of a field of view, and all the beam adaptation, beam steering, link adaptation, everything happens within this field of view, and the throughput widely varies depending on where your beams are pointed at within this field of view. It can go all the way from a gigabit per second to a few hundred megabits per second if you're operating on the fringe of the aperture versus you're operating in the center of the aperture, right? So there are a lot of variations into how these antennas are created, what kind of throughputs they provide. And to top it off, we have mobility of the UAV, right? So what this means is that the orientation, how you orient the UAV, which means how you've mounted the radios and the antennas on the UAV, will in turn have a large impact on the robustness of this directional topology. We go to millimeter wave, we have access to a lot of bandwidth, but the topology becomes really fragile, right? And not just the position of the UAV, but the orientation of the UAV also starts mattering at this point in time. A simple example, right? Let's say you had 3 radios to provide 360-degree coverage. Now, one orientation might not be efficiently using all the 3 radios, right? One of them might be wasted, and another might be multiplexing traffic from 2 UAVs. Now, if you change the orientation slightly, maybe that's better in terms of utilizing these radios much more efficiently and routing traffic, right? Now, the question is, how do you put these different aspects together? We're not just talking about routing, but we're talking about figuring out where to place the UAVs, how to orient them, and then route and manage traffic on top of these solutions, right? So even much simpler variants of these problems are NP hard, right? They do not admit an optimal solution in polynomial time. So how do we go about really coming up with a solution that can be orchestrated in real time? So that was essentially the goal of Skyhaul. I think I'm going to skip some of the details because I want to talk more about the applications that Skyhaul and Skylight as a whole can enable. I apologize for that, but I'll share these slides with you so that we can discuss these offline and over email if somebody is interested in these, right? I'll just very quickly point out the high level approach. So Skyhaul was designed to take a practical yet technically sound approach towards this problem, right? And it alleviates the coupling between the RAN and the backhaul through a functional split of the UAV's roles. Some are designated as application UAVs, while others as relay UAVs, right? While the hardware for both the UAVs are potentially the same, the application UAV's primary objective is optimizing the application directly. So it could be providing small cell connectivity. It could be some vision-based application for event detection. It could be anything, right? The application could be connectivity or sensing or something else, right? In this particular case, we are talking about connectivity. So the application is for the SkyRAN to optimize its own small cell connectivity. But as the application UAVs are free to adapt themselves to optimize their application performance, the role of the relay UAVs is to adapt their configuration to ensure a robust backhaul network that can serve the aggregate traffic. So it's like we decouple the roles with different objectives. We have these two objectives. We want to minimize the cost of the deployment or maximize the traffic, however you want to pose the problem. But the application UAVs have a lot more flexibility in targeting their primary objective, while the backhaul UAVs are responsible for maintaining this backhaul, right? And with these, we've come up with some very interesting algorithms that allow us to upgrade this. So I'll just skip these. So there are some particular ways in which we do these. There are some very interesting algorithms. I encourage you to look at the paper relevant to this for some of those algorithms. But it's not just the algorithms, right? Because at the end of the day, we are interested in migrating or creating these configurations autonomously without humans in the loop. And that means that we can't just stop at designing algorithms that find these configurations. How do you migrate the UAVs continuously to adapt to dynamics on the ground, right? For example, in a forest fire situation, as your first responders move from one section to another, your network has to evolve. And when it evolves to the new configuration, we equally care about this evolution happening in the shortest time, but in a safe manner. You now have to care about how to do a conflict-free migration in the airspace. So how do you resolve conflicts in the airspace? And there are some interesting ways in which we leverage the smallest number of altitude layers to quickly migrate these configurations and show that we can do this in an optimal amount of time in getting the new configuration up and running with as limited disconnectivity as possible. So we deployed this network on our campus with 4 to 6 UAVs. The access is LTE on a 10 megahertz channel. The backhaul is 360 gigahertz radios to provide 360-degree coverage on each of the UAVs. And then we've gone through like an entire, we did a complete network experiment where the application UAVs were instructed to emulate a scenario of tracking user population on the ground. Now, as the application UAVs move, we wanted to see how the relay UAVs adapt and how does it compare to another solution that doesn't do this intelligent adaptation, right? And this is a real live network result that I show on the right. When the application UAVs move, we deploy a relay UAV, right? The relay UAV automatically figures out where to go and position itself to immediately restore the lost throughput or the degraded throughput, right? And of course, once the application UAVs move elsewhere, the relay UAV figures out where to position itself to better load balance. And finally, when the application UAVs, if they were to move to a completely different section that requires a completely new configuration, then different layers of altitude are used to ensure this migration happens successfully, right? And safely, more importantly. So these algorithms are important because if you want to do it autonomously, you need to make sure safety is a prime criteria in the design to begin with. So we've designed some algorithms. As Yasmin was pointing out, you could do a lot more sophisticated things in the future. So this was partly because we also wanted these systems to work and adapt in real time. So there was always a trade-off between how sophisticated an algorithm versus how real time you can make these algorithms and how do you make them without any human intervention. So it's a trade-off between these different aspects. So right now, today, we can have like 3 to 4 hops, each hop being about 300 meters. So we can easily deploy like a 1 kilometer radius network today. That's for like a small scale city. We can provide like public safety, like a quick rescue kind of an operation. So that's what it was designed for. Now, so what I want to do is, let me just quickly go over some potential applications that we created with Skylight, right? So what I talked about so far was just connectivity as one application, right? That was the primary goal with which it was created. But if you think about it, it broadly provides network in the sky as a primitive or service, right? That can enable numerous connectivity and sensing applications. Anything that has like demanding bandwidth and latency requirements over a slightly larger area, we can use this, right? And the other cool thing is it has a very modular architecture. So which means you can create a very flexible composition of different interfaces. You can replace your LTE with Wi-Fi. You can take away some of the modules. If you don't need cellular, you don't need the SkyCore, right? You instead replace it with just a SkyRAN and SkyHall for Wi-Fi, right? Where the RAN would be the Wi-Fi in this particular case. And in cases where you don't even want connectivity, you want sensing, you can put in a LiDAR. You can put in a 4K resolution camera, for example. All these things can be composed within the same network, right? And you can compose different applications. And this was one of the reasons that it also drew a lot of interest from federal agencies, because there's a lot of interest in creating these standalone reconfigurable private networks, primarily for tactical operations, right? Because what happens if you don't have connection that you want to rely on something outside? Can you create something completely standalone that can be made secure and ruggedized in a way that serves the purpose for which it was created? So this is one such design that can cater to those needs. Now, another application we built was The first one we built was real-time video analytics, right? We have the ability to provide high bandwidth, low latency access to a larger compute on the ground, right? So this means that we can now pipe 4K and 8K camera streams from multiple sensors to be sent and processed by more sophisticated machine learning models on the ground, right? So this allows us to enable highly accurate object detection or other kind of event detection solutions at much higher altitudes than what you could do otherwise, right? So we are able to provide the backhaul needed to supply a lot of traffic back to much more compute resources that are available on the ground. That's a potential application. Now, you can also send 3D uncompressed LiDAR point clouds, right? They are fairly bandwidth intensive. So they can be made available to ground compute stations over Skyhawk. So what does this enable? This enables autonomous, accurate, and real-time 3D reconstruction of environments, which is a very tedious and offline process today. So if you look at startups that are doing this application today, the way they do it is they fly the drone, they collect these point clouds, you come back, and then you run it through a heavyweight computer vision pipeline that stitches these point clouds and creates the 3D environment, right? And then you look at it and you see that there are gaps in your reconstruction. It doesn't look good. So then you figure out you need to go and collect more data in a particular section of the environment. So now, having access to the Skyhall and this larger compute on the ground, we are able to do this whole process in real time. So what this means is that we start creating partial reconstructions as the data is being collected, and that is used to inform your trajectory so that we automatically identify if there are holes where more data needs to be collected, so that it ends up being just a single one-time effort. So you do fly it, but fly it intelligently, because we're able to bring this compute into the loop in this real-time data collection process. So this is an example of one such reconstruction we did in the campus building at NEC. Another application is your application UAVs. I talked about positioning users for connectivity, but look, localizing users could be an application in itself, right? We created one such tracking solution called Track.io that leveraged the UAVs, its mobility, along with RF sensing that comes from LTE interface if it's available, and also ultra wideband. And we use that to track first responders when they go into environments where they don't have access to any connectivity infrastructure, right? Or even GPS denied environments. So we can use that to track them and provide this information to ground stations where a commander, incident commander, can look at this information and make decisions in real time. So this was not just a research system and a paper, but it went further beyond that. And we are close to creating a commercial product that has been piloted with a lot of fire departments across the country today. So this is another application where we can tag specific sensing applications along with the ability to provide connectivity service in different environments. So with that, I want to summarize this talk. So what I want to say is essentially the fact that today engineering networks in the sky, although it looks like a bold vision, it is being pursued by numerous entities in parallel. And there's a lot of interest that's coming in both from the research domain as well as from the commercial domain. Of course, it faces a lot of big challenges, and the challenges not just span like point problems, but they span entire layers. And what I did was I tried to use Skylight, which is one possible solution, right? It's not the only solution. You can think of other ways in which you can create the solution. I used it as a backdrop to talk about how to design one possible way of a standalone 5G network in the sky, right? It's arguably a one-of-a-kind, first of its kind large systems effort that spanned multiple layers that worked in concert to make this happen. But of course, that doesn't mean it's a done deal. Numerous challenges still remain, right? But what it does show is its potential. The small set of applications I talked about so far, it gives us a very good glimpse of what potential it has for the future, right? It really opens the door for numerous on-demand connectivity and sensing applications in challenging environments. So with that, thank you for your time. I think I probably overshot it a little bit, but thank you for your patience. And if you're interested, this link carries some additional demos of Skylight in operation. So I'll be happy to take any more questions and any comments that you have.
Thanks, Karthik. So we have one outstanding question in the chat. So we have a question asking, how does, I think this is to do with the backhaul, how does the 60 gigahertz radio do beam search to compensate for UAVs moving around quickly?
Great question. So what we do is, so again, this operates at two levels, Zushi. One level is we figure out the configuration, and then the configuration is done to maintain connectivity based on the average case conditions, and then based on the field of view and the throughputs that we measure on the link, But what happens after that is once you create the link, you have all the beam adaptation, the beam steering algorithms that allow you to maintain the connectivity. Now, the next time things changes, and this adaptation is enough for the drone drifting a little bit or adjusting its orientation a little bit. But when we want to migrate it, at that point, we create diversity connections, which means we allow multiple connections from the UAV to multiple other UAVs, so that the diversity allows us to reduce the disconnections possible as you go from one configuration to another configuration.
Cool.
Okay.
Thank you so much. Yeah.
We have another question from.
Yeah, I see Jack's question.
Yeah.
Leverage proposed standard multi-hop routing mechanisms in the 5G IAB backhaul adaptation protocol. Yes, Jack. I think it can. This was designed a while back, but where IAB was still being designed, but you can leverage some of the IAB solutions. One thing to note though is we designed it for completely different technologies for access and backhaul. When it comes to integrated access and backhaul, they're going to use the same access technology. So definitely you can use some of those multi-hop routing mechanisms, because how you route, you can use any of the different protocols, but how you position the drones to facilitate this routing, you'll still have to address the problems that Skyhall addressed, because now it's no longer a decoupled problem. Where you position, how you form the topology, how much you decide to pipe traffic on different links, it's all interconnected.
All right. I think, as Karthik, you mentioned, we've overshot the time, so we should end there. So that's just remaining for me to say thank you so much for coming and talking, and to everyone else, have a great rest of your day.
Thanks,
Thank
everyone.
you for the